Hello everyone and welcome to the DTables.jl lightning talk at JuliaCon 2022. My name is Krystian Guliński and let's get started. DTables.jl is a package that provides you the distributed table data structures and operations that allow you to manipulate tabular data in a distributed environment. It's built on top of Dagger.jl and it's a good example of what you can build with its current capabilities. DTable.jl aims to be a solution to use instead of Dask for Python and Spark, and as of today it supports in-memory processing and it supports an experimental out-of-core mode enabled by Mempool's recent enhancements, which I'll be showing you later. As this is a lightning talk, we're keeping it short, so the key things to know about the DTable are: the DTable is split into chunks, so if you load a 30-row table into a DTable and specify the chunk size to be 10, it will be physically split into chunks of 10 rows and stored that way. These chunks can be then distributed across different processes and used in parallel. A data chunk can be of any type, so as long as your tabular type is compatible with tables.jl, you should be able to use it in the DTable as the internal storage solution. So right now the named tuple is most commonly used as an internal table type, but you can also use a data frame without any issues and all the operations will work exactly the same. The next thing to know about the DTable is that all operations are built to be executed in parallel from the ground up. So here's an example. If you apply a mapping function to the DTable1, it will actually apply this mapping function separately to each chunk of DTable1, and those actions can be executed in parallel but by available processes and threads. The results of these separate operations will then form the result, which is the DTable2. Lastly, the DTable is built to be compatible with the Julia data ecosystem. So that naturally means that the input and output is tables.jl compatible, so you can use any package such as CSV.jl or Arrow.jl to load and save the data in and out of the DTable. The syntax for basic operations such as map, filter, and reduce try to follow the syntax of base, but to make it even easier, we're trying to implement the DataFrames.jl mini language into the DTable. So select is already available and you can play with that right now. Also worth to mention is that the DTable actually works really well with online stats.jl for reduce and map reduce workflows. That's really worth checking out because you can actually do a lot of things with that already just by using these two operations and online stats.jl. Let's look at the timeline. The DTable has actually started as a proof of concept project inside the Dagger.jl repository last summer. We had the first release in December 2021 with some functionality already available. Afterwards, I spent a lot of time on benchmarking the DTables against Dask and Spark in in-memory scenarios. So these results are unpublished, but they look very promising and allowed me to gain more insight on where to go with this project. Meanwhile, some bug fixes and new features have dropped. But the latest news is that the DTables.jl is a package now. It's separate from Dagger.jl and you can add it through the package manager to your environment and have a go at it. As for the next steps, the most important item on the list is taking care of testing and tuning for Mempool's cache-to-disk capability, which will enable out-of-core data processing in the future. We also need more guides, a practical usage guide, an online stats guide, and a general out-of-core data processing guide for the DTables is something that we need. We also need to make the DataFrames.jl syntax support wider to increase the adoption of the DTables as much as possible. The to-do ideas list is here under this link. It's issue number 5 in the repository, so feel free to drop your ideas there as well. Okay, let's now move to the demo part of the talk. We'll be creating a data frame and then creating a DTable out of it. So now let's source the data from our dataset. These are test results, our datasets. And now let's create a DTable with 10 million rows and a chunk size of 100,000. this will result in creating a DTable with 100 partitions. First chunk that we just fetched is stored as a data frame, and that confirms that internally the DTable uses the type that was passed into it. We can get the full data frame that we passed back in any format that we want, by default in the internal type, but we can also just get it back in a named tuple. Now let's go to operations. We want to know what are the extreme values of the score column, so we're going to use online stats for that. The fit function here comes from online stats, and this init structure is also from online stats. So let's just run that and get the result. As you can see, we got it pretty quickly. And let's just check the coefficients of a linear function that we're going to use for mapping right now. So to create a mapping function, we basically need to create a function that takes a row and then returns a valid row as well, meaning a named tuple, ideally. So let's run that, and you will see that we're going to get another column called grade with this score column mapped accordingly, and we got it in the results. Now let's see how many of those grades are passing, so above 3. So let's just filter the data set, and let's just see how long it is after filtering. So about 25% of the records got filtered out during our filter operations. Now let's use something more complicated. This is a MapReduce example with group by from online stats. Meaning we will get a mean score per grade. So let's run that and let's look at the results. So as you can see in the REPL, we got 6 results per group. When it comes to group by, the interface is also simple. So here we're grouping by the first column Elia, and the chunk size we're setting it again because the data is being shuffled, and we don't want to create huge chunks of data that won't fit into memory of one process. As you can see, we got 179 partitions with 131 keys. That means that some keys have more partitions than one, which means data under that key is split into multiple chunks. That information is stored in the index, and that is used in operations that work on a grouped DTable. When you run reduce on a grouped DTable, the result comes back in a grouped format, so you will get essentially the same result as if you run it on a DTable, but per group. So as you can see, we got the mean grade per group inside the named tuple here. Lastly, we have the data frames like select, and as you can see, you can just normally use the data frame syntax. You can rename a column, you can pass a column, you can use by row functions which run in parallel, which is very good, but you can also use normal functions that run on a full column, but they don't run in parallels. And lastly, we have a function that just returns the thread ID. So as you can see, all threads that are available in the environment have been used for this operation. For the last part of the demo, I'll be showing you how the cache to disk capability of mempool works. So let's create a 3 GB DTable and set the memory limit to 2 GB, and then inspect the cache status on this. We should see a gigabyte of cached data on disk. So the allocator tells us that, but let's also look at the actual insights. So this small handy function tells us there's about 30 files with a file size of 30 megabytes, which checks out. Now let's also confirm that here. See, that's true. The way this will work is that any managed memory by mempool that doesn't fit within the constraints that we set will be sent to the disk and retrieved if needed by the DTable. So that's it for the talk. Thank you for watching. Make sure you check out the repository for updates, and have a nice JuliaCon. Bye!